In this video, we're going to look at the assignment to do search with Pacman. The code is available as a zip archive, and we have some instructions here describing the files that you'll be working with. There's an opportunity to simply try out the Pacman code. And so I can say Python Pacman, and it gives me a place where I can go, and I'm not very good at it, so I get eaten up pretty quickly. There's a simple reflex action example that we can show a simple rule of just go west. And that will work in that simple case, but it will not work in any more complex maze. So here we get stuck. The questions here start with a depth-first search, and there's a fair amount of discussion on how to do that. And if you follow that, that's fine. I'm going to start with breadth-first search, and the reason I'm going to start with breadth-first search is because the textbook provides pseudocode for that. Page 82, figure 311. There's a sample here where we can just show attempting to run it. And when we do, it fails quickly with a method not implemented at line 95. So, not surprisingly, here is our method not implemented. One of the first things that I'm going to do is just take some of the comments from their suggested output and place them here in our breadth-first search. Then I will try running the breadth-first search. It fails quickly as expected, but it does print out some interesting information. We can see the start is at 3416. Is the start a goal? False. And the start has some successors of a list of 2 tuples. With those as some ideas of how to proceed, let's take the sample code, the pseudocode, and paste it in as our sample, as our code, and comment it out. From there, we'll follow the instructions, the pseudocode. Node is an object with state equal to the problem initial state. Well, the problem start state is here. We'll also keep track of a cost of 0. So our initial node has a start state and a cost. Next, the pseudocode suggests if the goal test for the node state, then return the node. So if and have we reached the goal? Problem is goal state. If is goal state, and then the node state. Well, our node state. So if we're at the goal, and our objective is to return a list showing the actions to take. And if we're starting out at the goal, we don't need to take any actions. Next, we're going to set the frontier as a FIFO queue. We've been told in our instructions that there's stack, queue, and priority queue provided for us. FIFO would be first in, first out, and in utility we have a stack, which is last in, first out, and a queue, which is first in, first out. So we'll say util.queue and pick up one of those. Then the pseudocode says a FIFO queue with node as the only element. Frontier dot append add with node. So we're going to create a FIFO queue with node as the only element. Next, we're going to set up an empty set for explored. Explored equals set. So there we have an empty set. Now we are going to enter a loop while true. If the frontier is empty, return a failure. If frontier is empty. In that case, we're going to raise an exception and say search failed. Next, node is pop. Choose the shallowest node in the frontier. So node is frontier.pop. Add node state to explored. Explored, add node state. So we're going to add the node state. For each action, so now we want to look at the children, or the successors. Here I'm not going to follow the pseudocode exactly because we don't need to explore each of the potential actions. We're being given the successors that would be valid at that state. So I'm going to say successors is problem get successors for node state. So now we have our successors for successor in successors. Now we have our loop. Now we're going to create a child node. The child node, the suggestion for the pseudocode is that the child node be built based on the problem, the node, the action. So there's a function that would generate it. In our case, what information do we want to keep about the child? Well, we'll start out with state and use the successor. The successor will tell us something about it. What information are we getting from the successor? Well, we saw in our output that it's a tuple, a 3-element tuple with a state, an action, and a cost. So successor, the first element is the state. There's an action that is the next element, and there's a cost for the successor at the last element. We also could be interested in a parent. And we'll say that the parent is the node. So that gives us access to look up the tree as well. Next, if the child state is not in the explored group. So if child state not in explored. If the child is not in explored, if we've reached the goal, so how the problem goal test? Well, again, problem is goal state. Problem is goal state for the child state. If the child state is the goal state, then we want to return the solution. Some sort of list of actions. We'll come back to that in a moment. Otherwise, we want to insert the child onto the frontier. So now the child's been inserted on the frontier. So what we're left to complete this is we want to check the goal state. When we reach the goal, we want to return something. So let's say actions is a list, and now we want to step back through the current child and add each of the actions that it took to get here. And we'll return actions. We have a child, and each child has a parent. I'd like to be able to step through each of the parents. So what I'm going to do is I'm going to say node equals child, and then while there is a parent in the node, I'm going to add the action to the actions. Actions dot append of the node action. We've added the action to get to this node, and now we want to add the action to get to the previous node. So while the parent is in node, we need to move up the tree. So node is the node's parent. With the node's parent, now we will check to see if it has a parent, and eventually we'll reach the root node that does not have a parent. Then we'll have our list of actions, but those actions will give us a reverse order path, so we need to reverse the order. That will give us a reverse on the actions. So let's give this a try and see what it looks like. Okay, we got an error in line 101 saying frontier add node. So let's look at 101, and we should push the node onto the frontier. We found a path with 68, and we expanded 273 nodes. So that seems like a success. Let's take that then and try it out with the Autograder. The Autograder is supposed to evaluate our work. We'll try out the Autograder. Question 2 was the one that is supposed to be dealing with breadth first search, so it gave us 0 out of 3 for question 2. Let's go back and read a bit about what it says. Question 2 failed. They're giving us a picture. A is a starting state, G is the goal. The arrows mark the possible state transitions. This tests whether you extracted the sequence of actions correctly, even if your search backtracks. So the student's solution, the code that I actually ended up with, was moving from A to C, and then from C to G, which is, in fact, the correct solution. The complaint the Autograder has is that I expanded A, B, and C, A, B, and C, but they say I should have expanded A, B, C, D. So they wanted me to expand D after I had expanded C. There's an argument for why this should be done in other situations, but if we go back and look at the pseudocode from the textbook told us that if, as we're expanding, we find the goal, for breadth-first search, we can return immediately without adding it to the frontier and expanding others. You can see a discussion on this in the text, page 81, the bottom of the page. As soon as a goal node is generated, we know it's the shallowest node because all shallower nodes must have been generated already and failed the test. Now, the shallowest goal is not necessarily the optimal one, but technically breadth-first search is optimal if the path cost is a non-decreasing function of the depth of the node. This is on page 82. And the most common such scenario is that all actions have the same cost. With a breadth-first search, we're not considering costs. We're just simply reaching down until we find something. We're not choosing the nodes to expand based on cost. That will come in a later exercise. So for the time being, I'm satisfied that this is a good solution. I will be studying this further and give you an update. But you may take this and see where it takes you with expanding to the other searches.